All right, folks, let's get started. Welcome back to Theories of Decision at George Mason University. We are this week switching gears. We're moving on from our discussion of decision theory, which has been our focus for the semester up to this point, and all of our background on expected utility theory and probability. And moving on now to game theory. We're going to use many of the same tools that we developed in thinking about an individual making decisions, but we're going to apply them in a new context. We're going to apply them now in the context of individuals making decisions while thinking about what others are going to do as well. So decision theory looks at the case where an individual makes decisions in an uncertain world. Now we're going to look at the case where an individual or individuals make decisions on the basis of what they expect other players to do, other individuals with whom they are interacting to do. And we're going to start with zero-sum games. So let's start with a very general description of what game theory is. Osborne and Rubinstein say that game theory is a bag of analytical tools designed to help us understand the phenomena that we observe when decision makers interact with one another. The basic assumptions that underlie the theory are that decision makers pursue well-defined exogenous objectives. That is, they're rational. They are aiming at maximizing their expected utility, and take into account their knowledge or expectations of other decision makers' behavior. They reason strategically, and that's the new bit in game theory. That's what we're adding now, this idea of strategically reasoning about what other decision makers are going to do and how that ought to affect one's own behavior. So let's start looking at some classic games, just so we have some examples in mind. Rock, paper, scissors is a classic game that I'm sure we've all played. You're playing the game rock, paper, and scissors. Paper beats rock, rock beats scissors, scissors beats paper. Two of the same is a draw. Which do you choose? Well, which you choose depends on what the other player is going to do. It depends on what you think the other player is going to do. And what the other player is going to do depends, at least in part, on what they think you're going to do. And so what you're going to do, what you should do, depends in part upon what you think the other player thinks you're going to do, and so on. This is the structure of a strategic game. Let's look at another game. This is the game of Stag Hunt. We've encountered this before. Recall that Stag Hunt comes from Jean-Jacques Rousseau in his Theory of the Social Contract. He used Stag Hunt to think about how social cooperation may have come into being, how human beings could have come to understand social cooperation as rational. In Stag Hunt, you and an acquaintance have gone hunting, and you must each decide whether to pursue a large stag or to pursue a small hare. Alone, you can capture a hare. However, a stag requires two people to capture it. If you cooperate and both hunt stag, then you'll end up with much meat. But if you hunt stag while your acquaintance hunts hare, then you return home empty-handed. Do you hunt stag or do you hunt hare? Again, this depends on what you think the other player is going to do. We can explicate these informal interactive choice situations, these games, with formal mathematical models, just like we did in decision theory. A strategic game, G, is an ordered set that is composed of the following ingredients: an infinite set of players, N, a set of actions, A sub I, available to each player in the set of players, N, a set of outcomes, O, a function, G, that maps the action profile of each player within the set of players, N, to an outcome, O, in the set of outcomes. and a preference relation for each player over the set of outcomes, where O1 is preferred to O2, or is at least preferred to O2, just in case O1 is at least preferred to O2 by player I in the set of players. So the I here simply designates the player that we are talking about. So we have to define a preference relation now for each of the players in the game, just like we defined a preference relation for the decision maker in our basic decision models. Going forward, it's assumed that the preferences of each player in I in N are well behaved in the sense that they are representable with an interval utility function that maps the outcomes to the real numbers, to the set of real numbers. So we're just assuming that these are well-defined, well-behaved preferences that meet all of the axioms set out in expected utility theory. They are constrained in the way that expected utility theory requires, so that they can be represented by an interval utility function. We could model a situation where the outcomes of action profiles are affected by exogenous random variables as well, that is, by the way that the world turns out to be, by the way that the world behaves, by adding a set of states, omega. So we can integrate decision theory and game theory in that way. We can treat the world as itself a player in the game. The world itself, quote unquote, makes decisions. The game of rock, paper, scissors then would look something like this. There are two players, player 1 and 2. Each player has an action profile, rock, paper, scissors. There are 3 possible outcomes, 1 wins, 2 wins, or a draw. And then the G function maps paper, paper to a draw. The circumstance where player 1 plays paper and player 2 plays rock to 1 winning. The circumstance where player 1 plays paper and player 2 plays paper to scissors, or where player 1 plays paper and player 2 plays scissors to player 2 winning, and so on. We can see the entire G function laid out here. And then we have preferences for each of our players. Player 1 prefers 1 winning to drawing to 2 winning, and player 2 prefers 2 winning to drawing to 1 winning. Stag Hunt we can also represent as a formal model. Here again we have 2 players, player 1 and player 2. We have an action profile for each player. Here they only have 2 actions to choose from, hunt stag or hunt hare. We have a set of outcomes. Here we have 4 possible outcomes. They both get stag. They both get hare. 1 gets a hare, and in that case 2 gets nothing. And 2 gets a hare, and in that case 1 gets nothing. And we have the G function that maps the intersections of their action profiles to the possible outcomes. So hunt stag maps to they both get stag. Hunt stag, hunt hare maps to player 2 getting hare, player 1 going home empty-handed. Hunt hare, hunt stag maps to player 1 getting hare and player 2 going home empty-handed. And hunt hare maps to both of them getting hare. Both we have a preference relation defined for each player, player 1 and player 2. Player 1 prefers both get stag to both get hare, and is indifferent between both getting hare and just player 1 getting hare, and prefers all of those outcomes to player 2 getting hare and 1 going home empty-handed. We see the same thing holds for player 2. So a strategic game can also be visualized in a table or in a game tree, just like we did with our decision models. But we'll focus on tables except when considering games with sequential play. That is, games where one player moves, then the other player moves, and then the first player moves again, and then the other player moves again. Those are much more easily visualized in a game tree. But other games, the more simple games we're looking at, will be, or simultaneous move games we're looking at, will be easily visualized in a table. Generically, we refer to row player as row or player 1. So row is going to be player 1. And to column player as call or player 2. We can plug games in if we have, we can plug names in, if we have them. So we could give row and call names. For example, if we look at rock, paper, scissors, this corresponds to the following game matrix, where player 1 is row and player 2 is call, and player 1 can either choose rock, paper, rock, scissors, and player 2 can choose paper, rock, scissors, and we see the outcomes here. So very much like what we were doing with decision models. Just for reference, here's what rock, paper, scissors looks like as a game tree. So we see as a tree, the first action is done by player 1. Player 1 can choose rock, can choose paper, or can choose scissors. And then call player 2. If player 1 chooses rock, can choose rock, paper, or scissors. Player 1 chooses paper, can choose rock, paper, or scissors. If player 1 chooses scissors, can choose rock, paper, or scissors. Now, what's a little bit misleading about looking at this in a game tree is that it looks like there is a sequence of moves. First row goes, then call goes. And if that's the case, if row chooses rock, well, call would be crazy to choose anything other than paper, because paper covers rock. And so call would guarantee themselves a win. But that's not what we're looking at here. This is a simultaneous move game. That's what makes rock, paper, scissors the game that it is. It would be really boring as a sequential move game. So we need to keep in mind that this is mapping out the logical space of possibilities, but not the temporal space, as it seems to imply. So it's not a sequential game. Just for a bit of fun, here we can see what the game of chess looks like, where we are looking at a sequential game. White has the first move and can choose any of these possible moves. Black has the second move, and black can choose any of these possible moves. And then white has a move depending on that. So just 2 moves into chess and you already have 400 possible outcomes. In fact, no computer is powerful enough to calculate a solution to chess. Given the number of possible outcomes there are, the number of possible moves there are, computers can play the game of chess. Computers can use a number of heuristics and run a number of algorithms to competitively, very competitively play the game of chess. But there is no computer that can solve the game of chess. In fact, the estimated number of atoms in the universe is 10 to the 80. A supercomputer would take 3 times 10 to the 103, or 103 years to check out all these moves. The sun would die by then. The game of chess is simply too complex to solve even using a supercomputer. So games become, as they become more complicated, as there are more possible moves, the possibility space grows exponentially as those moves grow for each player. Those possibilities grow for each player. And so it can become very difficult very quickly to map out an entire game. If we then go ahead with rock, paper, scissors, we can substitute the pair of utilities U1 of O and U2 of O for each outcome in O in the matrix, and that gives us these utilities that we see here. The first utility in each ordered pair is always row's utility, or player 1's utility. So at paper, paper, row gets 0. And the second utility in each ordered pair is always player 2, or call's utility. So the first one is player 1, the second one is player 2. That's fairly straightforward. The game of Stag Hunt corresponds to this game matrix, so we can put Stag Hunt with row and call in a game matrix as well. And we could plug in utilities, and we would see something like this. At Hunt Stag, both players get 2. At Hunt Hare, Hunt Stag, player 1 gets 1, they get the hare. Player 2 goes home empty-handed because they tried to hunt stag but couldn't get the stag by themselves. We can also take some steps towards classifying games. So we're going to talk first about zero-sum games, or what are sometimes called strictly competitive games. A zero-sum game is one in which the winner's gain is equal to the loser's loss. That's what it means for it to be a zero-sum game. In order for me to get more, you have to lose something. A non-zero-sum game is one in which this criterion is not satisfied. It's one where it's possible that we both do better off, or both do worse off. Just because I do better doesn't mean you must do worse, and vice versa. A cooperative game is one in which the players are able to communicate with one another and to form binding agreements. And this will be important later on. We'll see why it matters that they need to form binding agreements. A non-cooperative game is just one that does not allow for communication and binding agreements. Games with no mechanism for enforcing agreements, so where the agreements might be made but aren't necessarily binding, those are non-cooperative games. A two-person game is one with just 2 players or teams. That's mostly what we're going to be dealing with, are 2-player games. An n-person game is any game with more than 2 players. So a 3-person game, a 4-person game, a 55-person game. All of these we could, in theory, represent in game matrices and in game trees. We could build mathematical models for. They get more and more complex to represent. We'll look a little bit at how one might represent n-player games or n-person games, but we're going to focus mostly on 2-person games. And finally, a simultaneous move game is one in which players select their strategies at the same time. A sequential move game is one in which players take turns, and so have knowledge of the other player's previous moves. We can also classify games as games of perfect information or games without perfect information. Perfect information games are sequential move games in which all players have information about the strategies played by the other players. So think about chess. Chess is a game of perfect information because you see each of the moves the other player has made. In some cases, we'll talk about games of complete information as well. Games of complete information are games where each player knows not only the other moves that the player has made, but what their preferences are, what their utility function is, and so can base their moves on, or can base their expectations about the other player's moves on what they know about their utilities. Symmetric games are those in which all players face the same strategies and outcomes. Iterated games are games that we play over and over again, rather than just one time, and this can dramatically alter the best strategies when compared to the same game played in a non-iterated way. We will see this when we look, for example, at Prisoner's Dilemma, that the iterated game is a very different beast than the non-iterated game of Prisoner's Dilemma. A game is said to be finite if and only if the actions available to each player is a finite set. Otherwise, it's an infinite game. More formally, looking now at zero-sum games, we can say that a strictly competitive or zero-sum two-player strategic game, G, is one where for any outcomes O1 and O2 in the set of outcomes, O1 is at least as preferred as O2 for player 1 if and only if O2 is at least as preferred to O1 by player 2. If player 1's preferences are represented with U1, then player 2's preferences are representable with U2, where U1 of O plus U2 of O equals 0 for all outcomes in O. So what that's saying is that a zero-sum game is one where player 1's preferences plus player 1's utility plus player 2's utility for each outcome is going to equal 0. If we think about a matrix, in each block of our matrix, the utilities for player 1 and player 2 are going to sum to 0. Rock, paper, scissors is a zero-sum game. Stag Hunt is not. Zero-sum two-player games are the most well-understood game by game theorists. They are the only games for which the math is pretty much complete and for which we can always specify a solution in terms of equilibrium strategies. They're also the easiest to understand, so that's where we're going to start. Okay, so now let's talk about what we're going to do with games. We've got a way of representing them. We see what they look like formally and what they look like in a game matrix and in a game tree. But what's the point of looking at these games? What are we trying to do with them? What we're trying to achieve in looking at games is something called a solution to a game. A solution to a game is a kind of prediction about how a completely rational player would play the game, or an ideally rational player would play the game. So what we're doing when we solve a game is finding the strategies that ideally rational players would play in that game. And then the assumption is that, given an assumption that the other player is rational, the player we're playing against is rational, we should play the ideally rational strategy. Now, of course, the assumption that the other player is rational is one that might be suspect in some circumstances, but it's a good place to start. So the most famous solution concept in a game, the most famous solution rule or solution concept in game theory, is the Nash Equilibrium. And I'm sure you've all heard of this before. Informally, a Nash Equilibrium is a set of strategies such that each player's strategy maximizes his payoff if the strategies of the others are held fixed. Thus, each player's strategy is optimal against those of the other players. Osborne and Rubinstein put it this way: no player can profitably deviate given the actions of the other players. That is, you cannot unilaterally deviate from the strategy that you're playing and make yourself better off. Given what you think the others are going to do, you're playing the best possible strategy you can. If that holds true for all players, then we've found a Nash equilibrium. More formally, we can say this about the Nash equilibrium. Let's let AJ and A not J designate the action profile where player J performs action AJ in the set of actions, and all the other players perform A not J in their own sets of actions. A Nash equilibrium of G is an action profile, A star in the set of action profiles, such that for every player J in the set of players, the following condition holds. The G of A J star or A star J and A star not J is at least as preferred by J to the G of A J and A star not J. for each AJ in the set of actions, in the set of action profiles. So this is saying that the action profile A star J is at least as preferred as any other action profile, or gives us outcomes that are at least as preferred as any other action profile, given that all of the other players are playing the strategy A star not J, or the strategy that we've set, that we expect them to play. Little note on notation: AJ is an action or strategy of one of the players J in the set of players, and A not J is an action or strategy of a different player, any other players. A star J is the proposed Nash equilibrium action for J. Now that sounds really complicated, and in some cases it is really complicated finding a Nash equilibria. But what we're going to look at in much of the rest of this lecture are some strategies for discovering these Nash equilibria in more straightforward ways. So let's start by looking at rock, paper, scissors. Does rock, paper, scissors have a Nash equilibrium, or have any Nash equilibria? Well, the way we want to think about this is to look at each possible set of outcomes. So look at each block in our game matrix and ask for each block whether either player could unilaterally deviate and make themselves better off. So let's start with paper, paper, 0, 0. Could either player, either player 1 or player 2, deviate from paper, paper and make themselves better off? Well, player 1 could make herself better off by playing scissors. So this is not a Nash equilibrium. How about rock? How about paper, rock? Well, here player 1 can't deviate and make herself better off, but player 2 can clearly deviate and make herself better off. So paper, rock is not a Nash equilibrium because 0 and 1 are both better than -1, given that player 1 is playing paper. All right, how about paper, scissors? Here we see that player 2 cannot properly player 2 cannot profitably deviate from playing scissors, given that player 1 is playing paper. Playing scissors is the best they can do. But player 1 can profitably deviate from playing paper, given that player 2 is playing scissors. They'd rather play rock. So paper, scissors is not a Nash equilibrium. Let's try one more. Let's look at rock, rock. Here it's 0, 0. Can either player profitably deviate? Well, player 1 can profitably deviate by playing paper, given that player 2 is playing rock, and player 2 can profitably deviate by playing paper, given that player 1 is playing rock. So this, again, is not a Nash equilibrium. In fact, if we checked all of them, none of these are Nash equilibria of rock, paper, scissors. There is no pure Nash equilibrium of rock, paper, scissors. There are mixed Nash equilibria, and we'll talk about those later. So let's move on to Stag Hunt. Does Stag Hunt have any Nash equilibria? Well, we do the same test. Let's start by looking at 2-2 at Hunt, Stag, Hunt, Stag. Does either player have incentive to deviate from Hunt, Stag, Hunt, Stag? Well, player 1 cannot profitably deviate given that player 2 is hunting stag, because 2 is greater than 1. Player 2 cannot profitably deviate if given that player 1 is hunting stag, again because 2 is greater than 1. So Hunt, Stag, Hunt, Stag is a Nash equilibrium of Stag Hunt. Is it the only Nash equilibrium in Stag Hunt? Well, let's look at Hunt Hare, Hunt Hare. Here, player 1 doesn't have any incentive to deviate. Given that player 2 is hunting hare, they don't want to hunt stag. They have to stick with hunt hare. And player 2 has no incentive to deviate. Given that player 1 is hunting hare, player 2 also wants to hunt hare. So hunt hare is a second Nash equilibrium of Stag Hunt. In fact, Stag Hunt has two Nash equilibria that give us different outcomes. One is clearly preferable to the other, and we'll see when we start looking at coordination games, or coordination problems, of which Stag Hunt is one, that this is a really difficult problem for the players to solve without being able to communicate or coordinate with one another. We'll move on. For homework, for a bit of extra credit, I'd like you to explain to me whether this scene from A Beautiful Mind, the barroom scene from A Beautiful Mind, is a good example of a Nash equilibrium. The link will be available to you, or is available to you, on the slides that will be posted on Blackboard. So go ahead and click through to this video on YouTube, watch the video, and tell me whether this is a good example of a Nash equilibrium, where, given the other player's strategies, given the strategies that you expect the others to play, you in fact have no good reason to deviate, or the player in question has no good reason or no incentive to deviate. And explain to me why this is or why this is not, in fact, a good example of a Nash equilibrium. Now let's move on. In a zero-sum game with players 1 and 2, row and call, U2 of an outcome is equal to the negation of U1 of that outcome. So we need include only the utility of player 1 in the game matrix. All we're saying here is that when we see a game matrix that looks like this, where the outcomes for player 2 are simply the negations of the outcomes for player 1, we only need to show the outcomes for player 1, or the utilities of the outcomes for player 1. And when we show only the utilities for the outcomes for player 1, we have to keep in mind that the utilities of the outcomes for player 2 are the negations of each of these utilities. So, does this game have any Nash equilibria? Take a second to work the problem and see if you can find a solution. See if you can find any Nash equilibria to this game. We might begin, intuitively, by looking at the greatest possible outcome, or the best possible outcome for player 1. The best possible outcome for player 1, for row player, is this 9 down here in the bottom left corner. So when player 1 plays A3 and player 2 plays A1, player 1 gets 9, player 2 gets -9. Is this perhaps a Nash equilibrium? Well, player 1 has certainly no incentive to deviate from playing A3, given that player 2 is playing A1. But player 2 certainly does have an incentive to deviate from playing A1, given that player 2 is playing player 1 is playing A3. Player 2 would much rather play A2 where they get 0, or A3 where they get 1, rather than playing A1. So it's not a Nash equilibrium. Player 2 has an incentive to deviate in this case. Is there another outcome we might try? Well, how about we start in the top left corner, A1, A1. Here, well, we see already that player 1 has an incentive to deviate. So that's not going to be a Nash equilibrium. How about A1, A2? Here, we see that player 1 has no incentive to deviate. They're going to get their best possible outcome by playing A1 if player 2 is playing A2. How about player 2? Well, here, player 2 does indeed have an incentive to deviate because they're going to get -8 at A1, A2, but if they move to A3, they're only going to get -7. They do a little bit better. So given that player 1 is playing A1, player 2 wants to play A3. How about A1, A3? Is that possibly a Nash equilibrium of this game? Well, given that player 1 is playing A1, we know that player 2 wants to play A3. So it is it is not a position that player 2 will deviate from. How about player 1? Given that player 2 is going to play A3, does player 1 have any incentive to deviate, to unilaterally deviate from playing A1? In fact, they don't, because they're getting 7 at A1, A3, and would do much worse by playing A2 or A3. So A1, A3 is, in fact, a Nash equilibrium of this game. It's the only one. But that is a really tedious way of trying to find Nash equilibria. So we're going to look at 3 methods to find equilibrium pairs for zero-sum games, zero-sum two-player games. So these methods help us to find Nash equilibrium pairs only for zero-sum two-player games. We're not going to be able to use them for other games, but for zero-sum two-player games, they allow us to find Nash equilibrium pairs. The first is dominance reasoning, or what we'll call DR. DR is an imperfect but sometimes fruitful strategy for solving games. To solve a game is just to determine, as we said, what rational agents would do when playing the game. DR is imperfect because it will not give a solution in every case, and because in some cases it leads to some unacceptable or strange outcomes. DR is sometimes fruitful because it can be used in both zero-sum and non-zero-sum games to give us a feel for the game that we're dealing with. It can help us to see how players themselves might think through the possibilities within the game, might think through their strategies. DR makes 2 key assumptions. It assumes that all players are rational. That's an assumption that we're making in game theory already. And it assumes common knowledge of rationality, or CKR. That is, it assumes that each player knows that the other players are rational and knows that each of the other players knows that each player is rational, and so on. So it assumes that we all know that the other players are rational and they know that we are rational. No rational agent, we assume, would play a dominated strategy. So this allows us to rule out strategies that are dominated. Once we've ruled out a strategy, we can redraw the matrix without that strategy included. This may in turn rule out strategies for the other player that are dominated in the new matrix. So let's look at some examples of this. Does this game have any Nash equilibria? Well, we might begin by asking whether there are any dominant strategies here. And what we find, so what do we find when we ask this question, whether there are any dominated strategies in this game? Well, let's begin by looking at row first. Do any strategies dominate any other strategies for row. Remember, row is player 1, so these are row's utilities right here. Does A1 strictly dominate any other strategy? No, it does not, because 10 is greater than 3. Does A2 dominate any other strategy? No, it does not, because 8 is greater than 1. Does A3 dominate any other strategy? No, it does not, because 8 is greater than 6, and 10 is greater than 5. So, no strategies for row are dominated by any others. Next, let's look at call. Remember that since it's a zero-sum game, call's outcomes are the negation of rows. Are there any dominant strategies for call for player 2? Well, here we might start by looking at A1. And for A1, 0 dominates, or 0 is better than 8, negative 8, and better than negative 3. 0 is better than negative 1, and better than negative 10. And 2 is better than negative 6, and better than negative 5. So A1 is in fact a strictly dominant strategy for player 2. It dominates A2 and A3. So we can ignore those two strategies. And call knows this, and row knows this about call. Player 1 knows this about player 2 because they know that player 2 is rational and isn't going to play any dominated strategies. So call will always play A1. Does this change things for row? Does row have a dominant strategy now? Well, row is definitely not going to play A3 because A3 is strictly dominated by both A1 and A2. Row would rather get 0 than negative 2. So row will play A1 or A2 since she knows that call will always play A1. A1, and A2, are both Nash equilibria of this game. You can have more than one solution to a game. And if we wanted to double check our work, we could go back to A1, for example, and ask whether, given that player 2 is playing A1, whether player 1 has any incentive to deviate, and it's clear they do not. And given that player 1 is playing A1, does player 2 have any incentive to deviate? And player 2 does not, because 0 is better than negative 8 and better than negative 3. So we can see these are in fact Nash equilibria. Another example. Does this game have any Nash equilibria? Let's look first at row. Does any strategy dominate any other? Well, here I'm going to speed through this a little bit. A3 dominates the other strategies, so row will play it, and call knows that row is going to play A3. Does call have any dominant strategies here, given that row is going to play A3? Well, call is not going to play A2 or A3 because negative 6 and negative 4 are worse than negative 1 and negative 1, so call is only going to play A1 or A4. So A3, A1, and A3, A4 are both Nash equilibria here. But are they the only Nash equilibria of this game? They're not. If we had started by looking at row's dominant strategies, we would have seen that row would only play A1 or A4. They strictly dominate A2 and A3. And if row is playing A1 or A4, then A3 is not strictly dominant for call, if call is playing A1 or A4, then A3 is not strictly dominant for row. Row could choose between A3 and A1 and guarantee the same outcomes. So A3, A1, and A3, A4 are Nash equilibria, but so are A1, A1, and A1, A4. Neither player would have an incentive to deviate from any of those four positions. This is just what I said. So there we see an initial problem with dominance reasoning. If we apply it and find some Nash equilibria, we can't assume that those are the only Nash equilibria in the game. It is sensitive to where we begin applying dominance reasoning, if we begin with player 1 or player 2. Dominance reasoning doesn't always give us all of the solutions to a game. It can also fail to give us any solution at all to a game, and sometimes can lead to unacceptable outcomes. Let's look for a second at the Centipede Game. The Centipede Game is a game between player 1 and player 2, where they take turns making moves. At the first node, player 1 can either move down and take 1, 0, the outcome where they get 1 and player 2 gets nothing, or they can move to the right and allow player 2 to choose, either going down to the outcome where player 2 gets 2 and player 1 gets nothing, or they can move, player 2 can choose to move to the right and allow the game to continue, in which case player 1 then gets to choose either the outcome where player 1 gets 3 and player 2 gets 1, or the outcome where or they continue the game and allow player 2 to make the choice. And it's very clear that the best outcome for both players is to allow the game to continue for a while. And at this last node, if player 2 continues the game, player 1 gets 6 and player 2 gets 5. And if they end the game by taking down here, player 1 only gets 4, but player 2 gets 6. Either of those outcomes would be preferable to these outcomes over toward the beginning of the game. But if we use dominance reasoning here, we find that the dominant strategy for row and call is to deviate immediately, to take the down move as soon as they have a chance. And we can see this if we do some backward reasoning about this game. So at this very last move that 2 has, we can assume that 2 is going to take down because they get a better outcome. They get 1 more util than if they take they move to the right. They get 6 instead of 5. Well, player 1 knows that, so player 1 is not going to allow player 2 to make that move. Player 1's going to end the game right here by taking 5 for himself and allowing only 3 for player 2. But player 2 knows that player 1's likely to do that and would rather have 4 than 3, so they're going to end the game right here and only give player 1 2 utils. But player 1 knows that and would rather have 3 utils than 2 utils, so player 1's going to end the game right here. But player 2 knows that and would rather have 2 utils than 1 util, so player 2 is going to end the game right here. But player 1 knows that and would rather have 1 util than 0 utils, so player 1 is just going to end the game right off the bat. Dominance reasoning leads us to a kind of unacceptable outcome of that game. So dominance reasoning is imperfect. Let's look now at the Maxima theorem for two-player zero-sum games. This is a theorem that helps us to find or to discover Nash equilibria for two-player zero-sum games, and it relies on the fact that these games have various nice properties. They're well behaved in a particular sort of way. The first of these properties is that two-player zero-sum games satisfy the Minimax condition. A pair of strategies is in equilibrium if, but not only if, the outcome determined by the strategies equals the minimal value of the row and the maximal value of the column. These solutions can be determined then using the maxi-minimizer method. And it is in fact the case that all maxi-minimizer strategy pairs are Nash Equilibria of two-player zero-sum games, and it is also true that all maxi-minimizer strategy pairs have the same value, and so we can call this the value of a two-player zero-sum game. The value of the game is going to be the utility that the maxi-minimizer strategy pairs have for player 1. So let's let min aj designate the lowest utility obtainable by performing an act aj in the set of action profiles for j. A maxi-minimizer for player j is an action a star j where the min of a star j is the maximum minimum for all action profiles of j. It's the maxi-minimizer for j. Then the maxi-minimizer theorem says that a star 1, a star 2, so the action profile starred for 1 and the action profile star for 2, is a Nash equilibrium of the two-player zero-sum game G only if a star is the maxi-minimizer for player 1 and a star 2 is the maxi-minimizer for player 2. So it's telling us to find the maxi-minimizers for each player. If they intersect, if they coincide, that's going to be a Nash equilibrium. So we recall here this game we looked at earlier. A1, A3 was the only Nash equilibrium of this game. And A1 is the maxi-minimizer for player 1. We find that by finding the min in each action for player 1. The min in A1 is 7. The min in A2 is negative 10. The min for A3 is negative 1. And 7 is the maxi-minimizer. So A1 is the maxi-minimizer action. And it is the maxi-minimizer. A3 is the maxi-minimizer for player 2. So we find that by finding the mins of each action for player 2. So the min for A1, remember there are negations in front of these. The min for A1 is negative 9. The min for A2 is negative 8. And the min for A3 is negative 7. Negative 7 is better than negative 8 and negative 9. So A3 is the maxi-minimizer. Since the maxi-minimizer for A1 and A3 coincide, or for player 1 and player 2 coincide at A1, A3, that's the Nash equilibrium of the game. Let's look at the other game that we looked at earlier. Recall that A1, A1 and A2, A1 are the Nash equilibria of this game. And if we do the maxi-minimizer for player 1, we find that A1 and A2 are the maxi-minimizers. The min for A1 is 0. The min for A2 is 0. The min for A3 is negative 2. 0 is better than negative 2, so those are both the maxi-minimizers for player 1. For player 2, 0 is better than, 0 is the min for A1. Remember your negatives, so this is a 2 now, so 0 is the min. Negative 8 is the min for A2, and negative 10 is the min for A3. So in this case, A1 is again the maxi-minimizer for player 2. So A1 is a Nash equilibrium where they coincide, and A1, A2 is a Nash equilibrium where these maxi-minimizers coincide. We can give a formal proof of this theorem, but I'm not going to work through it. It's there in the slides for you to look at if you're curious. And if a two-player zero-sum game G has a Nash equilibrium, then A1 star and A2 star are maxi-minimizers for player 1 and 2 respectively, only if A1 star, A2 star is a Nash equilibrium of G. That's just saying that if it has a Nash equilibrium, then the Nash equilibrium will be the maxi-minimizer strategies for both. It's a surefire way of finding a pure Nash equilibrium of a two-player zero-sum game. And Theorem 2.13 just says that if A1 star, A2 star, and A1 double star, A2 double star are Nash equilibria of the two-player zero-sum game, then they are Nash equilibria only if they have the same utilities. Less formally, all Nash equilibria of the game have the same utilities. The equilibrium payoff, V star, value star, to player 1 is, as we've said, the value of the game. And we can give a formal proof of that as well, but I'm not going to work through it. So the value of this game is 7. The value of this game is 0. And then we have what we call the coordination theorem for zero-sum games. A1 star, A2 star, and A1 double star, A2 double star are Nash equilibria of the two-player zero-sum game G only if A1 star, A2 double star, and A1 double star, A2 star are Nash equilibria of this game. And we can give a proof of that, but I'm also not going to work through that. This essentially just says that if A1 is a Nash equilibrium, and A3, A4 is a Nash equilibrium, then A1, A4 also must be a Nash equilibrium, and A3, A1 also must be a Nash equilibrium. That's what the coordination theorem is telling us. So we're going to leave off right there with two-player zero-sum games. We've now got dominance reasoning and the maxi-minimizer strategy, or the maxi-min theorem, for two-player zero-sum games. That is, we have now two tools for finding Nash equilibria of these sorts of games. We can work through dominance reasoning, and we can work through the maxi-min theorem, or use maxi-minimizers. Finding maxi-minimizers is going to be our most efficient method, our most effective method of finding pure Nash equilibria of two-player zero-sum games. The maxi-minimizer theorem is going to find those pure Nash equilibria anytime they exist for a game. What we'll look at next is the case where no pure Nash equilibria exist. And we will discover a strategy for solving mixed strategy Nash equilibria for two-player zero-sum games. But until then, we'll work through these strategies right here.